Hello, welcome to section 1.1 on linear models. Let's begin by investigating the following problem. Suppose your car runs out of gas. You'll need to purchase a gas can, which is $5, and some gas, which is $2 per gallon. We're going to start off by completing the following table, where we can see that the first row is the amount of gas we're purchasing in gallons, and C is the total cost we will have to spend at the gas station. First, how much we have to spend to buy no gas? Well, keep in mind in the problem, we are told that we are purchasing a gas can, which is $5. Plus $2 for every gallon of gas. But we're not buying any gas, so plus 2 times 0, because we're not buying any gas. So here, we would just be spending $5. Now, what if we decide to buy 2 gallons of gas? Well, again, we still have to pay $5 for the gas can, $2 for every gallon of gas, but we're buying 2 gallons, so we would have to multiply by 2. And if we work out the arithmetic, you'd have to spend $9 for gas. What if we buy 4 gallons of gas? Well, just like in the previous two parts, we still have to pay $5 for the gas can, plus $2 for every gallon of gas, but here we're paying for 4 gallons. Work out the arithmetic, and we have to spend $13 for 4 gallons of gas. Lastly, we decide to buy 6 gallons of gas. Well, just like before, we still have to pay $5 for the gas can, plus $2 for every gallon, so 2 times 6 since we're buying 6 gallons. Work out the arithmetic, 2 times 6 is 12, plus 5 is 17. Next, we're going to write a formula for the total amount we will spend. C represents how much money we're spending, and C will equal, well, let's think about how we filled out the table. We always have to pay $5 for the gas can. On top of that, we have to spend $2 for every gallon of gas. Well, if we let G be the amount of gas we're buying, we would have to add 2G on top of the cost. So our formula would be C equals 5 plus 2G. We're going to graph the equation on the axis provided. Now, we already know how much money we have to spend for various amounts of gas. We're going to make the horizontal axis how much gas we are buying, which is going to be G. The vertical axis, we're going to make the cost. If we decide to buy no gas, we have to spend $5. So we're going to plot a point right here at the point 0.05. One at a time, we're going to plot a point for each part of the table. Now that all my points are plotted, I can see that they're lining up quite nicely. So I'm going to connect those points with a nice straight line. And there we have our line. Now suppose we only have $23 in our pocket. We're going to write an inequality that will determine the possible number of gallons of gas we can purchase. Well, if we only have $23 in our pocket, the most amount of money we can spend is $23. So our cost of our gas must be less than or equal to $23. Otherwise, we won't have enough money. Well, we already have a formula for cost. We know the cost is 5 plus 2G. So the 5 plus 2G must be less than or equal to 23. And then from there, we can solve by subtracting 5 from both sides. We get that 2G is less than or equal to 18. Then divide both sides by 2, and we get that G is less than or equal to 9. So now we can see that if we have $23 in our pocket, the most we can buy is 9 gallons of gas. Now, in the last example, we took a look at the relationship between the amount of gas we purchase and how much we have to spend in 3 different ways. We looked at the relationship by first making a table, then we looked at a graph, and then we looked at an algebraic equation. In general, these are the 3 most popular ways to represent a relationship between variables from a verbal description. A table of values displays specific data points with precise numerical values. This is a great tool to help give us an idea of how the variables relate to each other. A graph is a visual display of that data. From a graph, it's much easier to spot trends and describe the overall behavior of the variables from the graph. For example, in the previous example, we can see that the more gas I purchased, the more money I would have to spend. The third method is an algebraic equation. An algebraic equation is a compact summary of the model. It's great because it can be used to analyze the model and to make predictions. An algebraic equation is also great for technology, where if we know what the algebraic equation is, we can quickly use technology to make a table of values or make the visual display in the graph. So in a lot of problems that we're going to be looking at later, we're going to want to find the algebraic equation first. That way, we can analyze its graph using technology such as Desmos. Linear models are models that can be represented by the equation y equals some initial value plus or minus a change times the variable x. X is the independent variable. This is the value we are able to manipulate. In the last example, G was used instead of X. We can use any letter we want. Typically in pure algebra, we tend to use X for the independent variable, but we can use any letter. Y is the dependent variable. Its value depends on what the independent variable is. In the last example, we use C instead of Y, C being the cost. Again, we can use any letter we want. And in the previous example, C depended on how much gas we spent. The initial value is the value of Y when X is 0. In the last example, we saw from the table that when x was 0, we had to spend $5. So what is the initial value in the last problem? That was $5. The change is the value that y increases or decreases by when we increase x by 1 unit. In the equation, we use plus when y is supposed to increase when x increases, and we use the minus when y decreases when x increases. So thinking back to the last example, what was the change? In the problem, we were told that for every gallon of gas, we had to spend an additional $2. So our change was $2. Now, by identifying the change and the initial value, we are able to use the form of the linear model to quickly come up with the equation. C equals 5 plus because of the increase, to G, which is precisely the equation we had in the last example. In this problem here, an airplane is at an elevation of 2,000 feet. It descends or goes down at a constant rate of 100 feet per mile. First, we want to write a formula for the airplane's elevation. Now, we're going to let y be the airplane's elevation based off of what we see in the table below. Now let's think about how we'll calculate the elevation. The airplane starts at a height of 2,000 feet. For every mile it travels, it's going down 100 feet. If we travel x miles, that means we lose 100x feet of elevation. So we'll subtract 100x from the 2,000. So my equation that'll tell me the elevation of the airplane is y equals 2,000 minus 100x. Now that we know the formula, we can use Desmos to help us with the other two parts. The next part is they want us to complete the table. If we go to Desmos, we can make a table by first clicking the Add Items option located here where the plus sign is, and then select Table. In the first column, we'll replace the x sub 1 with whatever we named our independent variable, which here we named it x. In the second column, we're going to replace that with the formula. Our elevation is 2,000 minus 100x. Now below the x column, we're going to enter our values of x we want to figure out the value of y for. So 0, 1, 2, and 3. Notice how underneath our formula, the numbers are populated. This tells me when x is 0, my elevation is 2,000. When x is 1, my elevation is 1,900, and so on and so forth. Here, we can quickly fill out our table. And we can also graph the equation. So going into the second option here, we'll type in our formula. Notice right now, nothing has populated. So let's shrink and hide our list of equations. If we zoom out, you can begin to see the purple line. Now, it's kind of hard to see it right now because of how thin it is, but if we go to the graph settings, we can change the scaling for our xy axis. So for our x-axis, let's make x range from 0 to 50, just to start out. Now, what about our y-axis? Let's go from 0, and since our initial value is 2,000, let's start with 2,000. Now we can see our graph. And we can see here that the line cuts off here when x is 20, so let's shrink the 50 to maybe 25 instead. Now, one of the benefits of Desmos is not only how quickly we can manipulate the window to fill in our graph, but we can also move around our graph and zoom in and out as much as we need. Now let's talk about intercepts. A graph can have two types of intercepts, an x-intercept and a y-intercept. The x-intercept are points where a graph crosses the x-axis. Points that are on the x-axis are always in the form of a 0, where a is some number, but the y component is always 0. So if we ever want to find the x-intercept from an equation, all we would have to do is set y equal to 0 and then solve for x. Y-intercepts are points where the graph crosses the y-axis. Now, points on the y-axis are in the form of 0b, so we can find y-intercepts by setting x equal to 0 and solving any equations we need to. In this problem here, suppose you want to purchase some fruit for the week. An apple costs 25 cents each, and a banana costs 10 cents each. You only have $5 to spend. First, how much will X apples cost? If I go to the store and I purchase X apples, each apple costs 25 cents. So the cost for X apples would be 0.25 times the number of apples that I'm buying, which is X. So the cost of X apples would be 0.25X. Next, how much will Y bananas cost? Well, each banana costs 10 cents, or $0.1. If I buy Y bananas, each at 10 cents, the amount of money I would have to spend for Y bananas would be 10 cents times the number of bananas Y. So I have to spend 0.1 Y dollars for Y bananas. Now we're going to write an equation for the total cost of X apples and Y bananas. Well, we know it costs 0.25X for the X apples and we know it costs 0.1y for the y bananas. Well, for our total cost, we would have to add them together. So the cost to buy the x apples and y bananas is 0.25x plus 0.1y. But I have to spend $5. So this cost with the variables has to equal 5. So my equation is 0.25x plus 0.1y equals 5. Next, we're going to find the intercepts of the graph and explain their meaning. Now, first, let's find the x-intercept. Recall we set y equal to 0. So replacing y with 0 in our equation, we have 0.25x plus 0.1 times 0 equals 5. Well, the best part of working with 0.1 times 0 is 0. Anything plus 0 is itself. So we're left with 0.25x equals 5, both sides by 0.25, and we get x equals 20. Now, what does this mean? How can we interpret the x-intercept? Well, for the x-intercept, we made y the number of bananas 0. So here, we're buying no bananas. So if we buy no bananas, how many apples can we buy? Well, recall x represents the number of apples. So if we buy no bananas, we can buy 20 apples. Now let's find the y-intercept. Y-intercept is when we set x equal to 0. So replacing x with 0, we have 0.25 times 0 plus 0.1y equals 5. Just like when we were finding the x-intercept, we have multiplication by 0. Anything times 0 is 0. Anything plus 0 is itself. So our equation simplifies to 0.1y equals 5. Then divide both sides by 0.1, and we get that y equals 50. How can we interpret the y-intercept? Well, to find the y-intercept, we made x 0, and x represents the number of apples. So here, we're buying no apples. Well, y represents the number of bananas. So when x is 0, y is 50. So when we buy no apples, that means we can buy 50 bananas. There are several different ways to write an equation for a linear model. The first two examples we did involve the change in the initial value. And we're going to call this form now the change in initial value form. It does have a formal name of slope-intercept form, which we're going to formally define in a future section. But our change in initial value form is the y equals initial value plus or minus the change times x. The last example we did, our model was in the form of what we're going to call general form. That is ax plus by equals c, where here a, b, and c are all real numbers. A third way to write our model is in what we call intercept form. If we know the intercepts of our model, the points a0 and 0b, we can use these to write the equation of the line in the following form. And that form is x over a plus y over b equals 1. Now, this is a special form of the general form. It's not the most appealing to look at because of the fractions, but we'll see how after we have the intercept form, we can quickly get to general form. In this problem here, we're going to write an equation from the given graph. We're going to leave our equation in general form with integer coefficients. Now, taking a look at the graph, we can easily identify what the two intercepts are. The x-intercept, where the graph crosses the x-axis, is the point 4, 0. Down here, we can see the y-intercept is 0, negative 6. Now that we've identified the intercepts, we can write our equation in the intercept form. That would be the x over a plus y over b equals 1 form. Now, from our work with the graph, our x-intercept is 4, so 4 is a. Our y-intercept is negative 6, so that will be b. So now we can put the values of a and b in the appropriate spot, and we get x over 4 plus y over negative 6 equals 1. And then we can do a little cleanup with the sign. Now, even though this is technically also a general form, because the intercept form is a more specific form of general form, they are very specific in the instructions that they do want integer coefficients. The way we're going to get integer coefficients is we're going to multiply both sides of the equation by the least common denominator. Well, if we look at 4 and 6, the least common denominator of 4 and 6 is 12. So we're going to multiply both sides of the equation by 12. On the left-hand side, we're going to distribute, and we get 12x over 4 minus 12y over 6 equals 1 times 12, which is 12. Now we can do some simplifying. 12 divided by 4 is 3. 12 divided by 6 is 2. So we're left with 3x minus 2y equals 12. And there is my general form where the coefficients a, b, and c are integers. To check to make sure we're correct, we can use Desmos. First, I'll check our intercept form, which is graphed here in black. You can see the intercepts are 0, negative 6, and 4, 0, which is exactly the same as what we have on the graph provided. Now, if we check our general form, well, we can see that the general form also has the same intercepts. Also, most importantly, you can see that the lines overlap.